Well, welcome back to the channel. This is just a quick video on how the Heathkit C-3U works in the leakage test mode. Hope you enjoy. Right, here we are. This is the circuit stripped out so that it's just showing the connections required for testing a cap for leakage. Nothing else. All the other parts here you see are blank. Let's start looking at what we know. We have a transformer. Paperwork says it's 500 volts AC. So what do we know about that? Well, we know that the 500 volts AC gives us a reading of 707 volts peak, which is what we'll be seeing on here. The old circuit had a selenium rectifier here with 26 or 25 separate elements, and each element is said to drop 1 volt. So we're expecting about 25 volts or 26 volts across there. So let's err on the side of caution and say we have 26 volts across that stack. Now, what does that leave us with? Well, that leaves us with 681 volts across those two capacitors there. 707 volts minus 26, so 681 volts. Now, using Ohm's law, we know that there's 47k there, but across here, if we add them all up, we know that it comes to effective resistance of 101.7k across there. And of course, Ohm's law also tells us that if we have 681 volts across 148.7k, that one and that one in series, we will get 4.58 milliamps flowing down here. So again, using famous Ohm's law, we will now know what the voltage is at this point, and the voltage at that point is 215.3 volts DC with respect to earth, measured across that resistor. This is a strange circuit because it references earth to the center of a divider chain, and so we know that the voltage on this side, if you've worked out the current down there as well with Ohm's law, it's going to come out as minus 465.8. So a bit bigger than the 415 they claim on there. And if we keep on looking at it, they say that that's a 5 volt tap off. And so if we measure 4.58 milliamps flowing through 1k, the voltage across it is going to be 4.58. So 4.5, 4.6 volts should be 5. And if we go along working it up, we'll find that each time we look at the taps with the current flowing, we are getting close to the voltages that they state in the book. So that's the first part. This 215 volts is also putting some current into the anodes of the EM34, which is the magic eye tube. And now the magic eye tube, I'm not sure how well this comes out, it seems to have two angles of shadow, angle 1 and angle 2. And they have effectively different gains. So it says they're both fully open, as wide as they can go, with 0 volts on the grid, reference to earth, or reference to the cathode. Now, to close the top shadow, the datasheet says it closes with minus 4.2 volts on the grid. Yet for this one, angle 2, the datasheet says it closes with minus 12.5 volts on the grid. So the difference in these angles give you a bit of a clue as to what the voltage on the grid is. And so now you say, well, how do we get this voltage on the grid? Well, you look here, the selector switch picks 5, 25, 150, 250, 450 volts and it comes to here. Now if you're using paper and mica, you're going to have a lot less leakage current. So what they do is they protect it with a 220k in series with the voltage, and then we follow it down, and in normal mode you see that's open, but when that lever, when you switch to the leakage mode, it's connected to there and it comes out on the cap connector. So that's how the voltage gets to the capacitor. Now the return path is the common, and the common comes back in, and you see that in normal mode there are two connections, but when you've pushed it down into leakage you join 3, 2 and 1 together, so you get 3 connections, which means the return current comes in on 3, it goes out on 2, it comes down here, and again with paper and mica that switch is open, so the 470k is in series with the 1k, and that gives you a more sensitive reading, and it's down to ground. And so what's happening is, if you also follow this back to the switch, you find that pin 1 goes into the grid, onto the grid. And so as the current, the leakage current flows through here, it generates a voltage across these resistors, which is a negative voltage, because these voltages are all negative with respect to ground, and so they drive the gate more negative, which closes the angles that you would see. And then you're wondering, well, okay then, so we now know how the circuit works and how it detects it. How does it make it safe? Well, you'll notice that this part of the switch here, one side of it connects to the common when it's in normal mode, so it connects up here to the common. The other side goes up, and in normal mode it connects to the capacitor. So as soon as you let go of that switch and it returns by spring back up, straight away when you're in the leakage positions, it switches that 2k resistor across the capacitor, and so that's how they discharge the capacitor and make it safe. And you can see that resistor is only really in circuit when it's in the leakage positions on the main switch. And so if we go back to this current path, if we've got it in the electrolytic setting, that switch will be closed and we'll have a 1k. And so it's quite easy from there with 1k to say that to fully close angle 2 you need 12.5 milliamps flowing through that resistor to earth, and to fully close the angle 1 you need 4.2 milliamps flowing through that 1k resistor to close it. So it's expecting quite a few milliamps of leakage across that through that electrolytic capacitor. In micra and paper, give it a quick calculation. So this say minus 4.2 divided by 471k. We're looking at approximately 9 microamps. So 9 microamps will fully close angle 1. And angle 2 will considerably higher. You can work it out for yourself. Minus 12 volts divided by 471k. So if you found this interesting and you want to see more, click on the subscribe button, give it a thumbs up, and click on the notification bell to catch further episodes or further videos. Catch you on the next one.